Good morning. Today we will discuss multiple linear regression model adequacy tests. Model adequacy tests. Okay. So, what we have learned so far about multiple linear regression? We have seen that the general equation is like this: beta 0, beta 1 x1, beta 2 x2, beta p xp plus epsilon, and which we can write in terms of x beta plus epsilon. We have already estimated the value of beta, which is x transpose x inverse x transpose y, and we also estimated the expected value of beta cap, which is beta, and covariance of beta cap, which is actually s square x transpose x inverse. We also have seen the epsilon cap, which is basically y minus y predicted, and this one we have seen in terms of I minus h into y, and we also have seen expected value of epsilon cap is 0 and covariance of epsilon cap, that is s square into I minus h, where h is the hat matrix, which is x into x transpose x inverse x transpose. Up to this much we have covered, and we want to test today that the model whatever we will develop under this equation or this equation, so whether the model is adequate enough to explain the data given. So, in this light, today's contents are goodness of fit test, test of individual regression parameters, and test of assumptions. These three things we will consider. Let us see first the goodness of fit test. In goodness of fit test, we will use one statistics called Rsquare, which is known as coefficient of determination. This will give us a ratio of explained variance, definitely variance of y by unexplained by total variance, unexplained plus explained by total variance of y. Okay. So, that means what we mean to say that y is having the y values, they vary from one to another, and there is variance of y which is s y square. S stands for the standard deviation, and related to y to the power square, that is the variance. Then the total variability in y, if we define like this as a t sum square total, that will be your n minus 1 s y square, where n is number of observations. Okay. So, this total variability will be decomposed into two parts: model explained variability plus unexplained variability. So, what we will be doing now, that SST can be decomposed into SSR, that R stands for regression, that is sum square regression, plus what is unexplained, that is sum square's error, and this one is the sum squares total. So, all related to the dependent variable we are talking about. We are talking about SST sum square total for y, and then this variability is explained by regression equation. The explained portion is coming under SSR, unexplained portion is coming under SSE. It is similar to the ANOVA what we have seen, the same thing. Okay. So, in order to establish this relationship, let us explain in with one variable, let it be that y versus x regression line, let it be like this. So, this one is your y cap, and let there is one observation of xi, that is ith observation on x. Then if you want to predict what will be the expected value of yi, expected value of yi given x equal to xi, this is nothing but this value. So, and this one is the predicted value of y. So, this is yi predicted. Let the original value of that yi is somewhere here. This is the observed value. So, observed, this is fitted, and let us also define the average. Let the average of y is here. Okay. Actually, it can be little up. Anyhow, you just assume that it is here. Then this value is y bar, this value is yi cap, this value is yi. So, what is this value then? Yi minus yi cap. This value is nothing but error value, correct. Then what is this value? This one. So, if you have no information about x, that means you have only information about y, then the best fit value is y bar. Suppose you want to say what is the next value, you will consider y bar. As x is available, as a result what is happening, you are able to find out some fitted or predicted value yi bar, I cap, and definitely it is what I can say, that closer to yi, which is the observed one. So, that means this is the amount for yi which is explained by the regression line. If there is no regression line, that means no x information with you, you will go by y bar. Okay, this is the if you have only the y information, this is the best fit. So, then this amount, what is this yi cap minus yi bar, this is what is explained by the regression line. Then yi minus yi cap, which is error, cannot be explained by the regression line when you are talking about one variable case, x equal to 1, y equal to y is always 1 in multiple regression. So, then if I want to write this yi, can I not write like this y bar plus this one plus this one plus this one. So, yi yi cap minus plus yi minus yi cap. You can write like this, y bar cancelled out, y I cap and yi cap will be cancelled out, yi will be there. So, if you recall the ANOVA part, then you can very well understand that what we are going to do, yi cap minus y bar plus yi minus y bar cap. You require to square the terms first, then take summation over all observations. You will be getting this square plus this square, definitely sum of this square plus sum of this square plus some that cross product, that portion will become 0. So, ultimately it is similar to your this one, that ANOVA part. So, what will happen ultimately, you will get something like this, I equal to 1 to n equal to I equal to 1 to n y I cap minus this square plus I equal to 1 to n y I minus y I cap whole square. So, what is this one? This is our SST, because if I want, I have y with y1 to like yn, I equal to 1 to n, and I am asking you what will be the variance component here. You will say that 1 by n minus 1 into yi minus y bar square, that is sum I equal to 1 to n. This one is nothing but this quantity yi minus y bar square, this is, that is SST by n minus 1. So, this is SST. So, similarly, this one will be SSR, because this is the amount which is basically explained by the regression. Then this is another amount which is quantity which is not explained by the regression. So, similarly, what will be your degrees of freedom here? N minus 1. What will be the degrees of freedom here? How many parameters you are estimating? P plus 1.
Yes, P plus 1.
So, P plus 1 minus 1, that will be P. Then what will be the degree of freedom here? N minus P minus 1. Getting? So, for total y, the SST part, sum square total, as you have n observations, n minus 1 is the degree of freedom. You are estimating P plus 1 parameter including intercept. So, that is why P plus 1 minus 1, this is the degree of freedom, in SSE this n minus P minus 1, this is the degree of freedom. So, then what is R square? R square is explained variance. What is explained variance? SSR divided by unexplained total variance, that is SST. Getting me? So, this R square value should be greater than equal to 0.90 for engineering application, or if you do experiments, laboratory experiments. But if you collect data from field, maybe less than 0.90 is also acceptable, because you are collecting data from field which is more more variable in nature, more dynamic, more volatile in nature. So, there what will happen, ultimately it will be very difficult to get R square equal to 0.9, you may get less, but even then you can go for, suppose for social sciences social, administrative, management sciences, it can be less than 0.90, but it all depends on the accuracy required. Okay. Now, in R-square there is one problem. The problem is, if I write down R-square little bit different way, that this is SSR by SST, which is SST minus SSE by SST, because this is quite obvious. So, 1 minus SSE by SST, correct. What is your SSE? In last class, I think last class only, I told you that SE square equal to SSE by n minus p minus 1. We have shown this one. So, instead of SSE, I will write SE square n minus p minus 1 divided by SST. I can write SY square into n minus 1. You see, SY square equal to SST by n minus 1. So, SST equal to SY square into n minus 1. So, you can write in this manner. Now, condition is like this, that n equal to p plus 1. What will be the value of R square? 1 minus AC square into n minus n, because n equal to p plus 1, divided by SY square n minus 1, this is 0. So, it is 1. So, this is the limiting condition. Basically, what will happen if your number of observation is equal to number of parameter estimated, your R square will become 1, saturated. So, that means R square is sensitive to n and p, and you require n much greater than p to rely on R square. So, in multiple regression, what it is said, that it is expected that n is will be like this, less than equal to 5p, not less than, it should be, what I meant to see, it should at least be greater than equal to 5p. Desirable is 10p, and if it is more than 10p, no problem, but again very large n also not desirable in many cases. Suppose if you go for chi-square test, sometimes in later part of the lectures we will see that chi-square will be used in some places. Then there, if chi-square is also sensitive to sample size, more sample size also not good there. So, okay, but for regression purpose, what I mean to say here, that if your sample size is at least 5 times of p, that is the starting point, you have to have this amount of data, and 10p is the desirable one, and in no case ultimately it should be less than 30. Suppose there is only 1 p, so that means you may think that it will be 5 into 1 5, that is not the case. So, I can say that the minimum value is 30, minimum n equal to minimum of 30 and 5p, whichever is minimum, maximum of this you write. should not be minimum, maximum of this 30 and 5p. Okay. So, in order to avoid this that dependency on n and p, if we modify r square in this manner, what will happen? We have written this r square equal to 1 minus s square into n minus p minus 1 by s y square n minus 1. Let us create one more statistics r a square, which is known as adjusted r square. In this manner, this divided by s s e by n minus p minus 1 and s s t by n minus 1. That means the sum square error divided by its degrees of freedom, sum square total divided by its degrees of freedom. Then what will happen? You can write s square n minus p minus 1 divided by n minus p minus 1 by s y square n minus 1 divided by n minus 1. So, n minus p minus 1, n minus p minus 1 will cancelled, this also will be cancelled. So, it will be 1 minus s square by s y square. It is irrespective of sample size, it will give you a value, and this is r a square. So, adjusted r square, which is known as r a square. This is parsimonious measure. This is known as parsimonious fit measure in case of multiple regression. Okay. So, with this we want to see that the example we are discussing, the same example, and what are the values. This is the data we will be using, and here sales volume is our y, absenteeism and missing breakdowns, these two are independent variables for explanation of multiple regression. Then last class we have fitted this one. We found that y equal to 130.22 minus 1.24 x 1 minus 0.30 x 2 plus error. This is my regression line. Using this regression line, you have found out the fitted values. Getting me? Basically, how you got these fitted values? We are saying y equal to x beta cap. What are your x values? X values 1 1 like 12 values. Then x 1 values are there. X 1 values are absenteeism and machine breakdown. So, absenteeism like 9, 8 like this up to 6, and breakdown hour 62, 58 like 60. This is your x. You have computed beta. What is the beta cap values? 130.22, then minus 1.24, minus 0.30. So, this one is 12 cross 1 to 3, then this is 3 cross 1. So, what you will get? You will get a 12 cross 1 vector of y cap. This is what is fitted values. Okay. You see in the fitted values are 100.44, 102.88. So, like this you will be getting up at the end 104.42, 104.77. Okay. So, what we require now, that fitted values are there, y is also available, you require to calculate SSR, SSE, SST. That is our work. Now SST you will be calculating very well like this, using this n minus 1 into sy square. That is the formula. Now if you want to calculate SSE, you require to find out what is the residuals. These residuals will be, this is y minus y cap. So if you will be getting already y values are there, y values are 100, 110. So in the same manner 12 values 103 and 110. Then fitted values you got 100.44, 102.88. In the same manner you will be getting here 104.42, 104.77. That means finally the error values will be minus 0.44, 7.12. Same manner you come minus 1.42, 5.23. So you have your error part also. So from here y value you calculated this one. From this you can calculate SE square. Getting me? How do you calculate? So our epsilon cap is n cross 1. If I make, you want to calculate SSE, which is epsilon cap transpose epsilon cap. SE square is epsilon cap transpose epsilon cap by degree of freedom n minus p minus 1. So this value will be epsilon t, this value will be around 155, I think 153 point something 68, by n is 12, p minus 1 is 3, so 153.68 by 9. So it will be 17.05, let it be. Similar, this value will be there. Okay. So then SSR, now we have to find out SST. SST value, we have to check SSE. I calculated. SST value will be 324.92. How do you calculate? Same way, your y is n cross 1. So 1 by n minus 1, if you do y transpose y, you will be getting it. I think y minus y bar transpose y minus y bar. This one you have to do. But here we have not done this manner, but we assume that this will be 0, but actually when you calculate that expected value of epsilon, that may not be 0, because your data is this one, data is this. So what will be the expected value? That is mean value, that sum of this epsilon I cap by n. It is theoretically it should be 0, but it may not be 0. Okay. And if you calculate like this, I think this value will be 155.
Consider that
0, that mean value is 0, then this will become 155. I calculated. Okay, but there is definitely that slight difference will be there because of small data set. Other way this should follow, even though that expected value of epsilon cap is not 0, but it should not be high value. Okay. So, using this SST you will be you are able to calculate SST. SST is this one. I was talking about S y square equal to this by n minus 1 equal to this. Correct. So, then SST is known. So, SST is y minus y bar transpose y minus y bar. This value we have found out that 324.92. So, my SSR is SST minus SSE now. So, 324.92 minus 153.68, which is 171.23. Okay. So, SSR is known, SST is known. So, R square value will be SSR by SST, which is 171.23 by 324.92. It is 52.7%, 0.527 less, very less. Okay. Then what is your R square value? This is 1 minus SSE by n minus p minus 1 by SST by n minus 1. So, that is 1 minus SSE is how much? 153.68 divided by 9, that is the degree of freedom, by SST is 324.92 divided by 11, n minus 1 11, and this quantity is 0.422. So, from 0.5 to 7 to 422, it is a I think reasonable change. This is because your n is only 12. This is because of this value. This change is there. See, R square drastically changed to 0.42 from 0.5 to 7. Okay. Now, what can you conclude from this? Straightway you can say that as R square is 0.5 to 7, this model is not fit. What I said, R square should be greater than equal to 90. Similarly, R square should be greater than equal to 0.90. So, both the things definitely whenever you will get R square greater than R square greater than R square. That should know that you get or not, you will not get. It may be R square equal to less than equal to R square less than equal to R square, and that is what is happening here. Okay, whatever in this particular example it is not fit, but some example it will you will fit it, that you get a good fit. So, here using R square you will basically, or this SST SSR, you are what you are creating here, you are creating a ANOVA table. You see the ANOVA table, analysis of variance, source, regression, residual, oblique error, total. Degrees of freedom, there are 3 parameters to be estimated. So, 3 minus 1 2, residual error is 9 because total degrees of freedom is 11, 11 minus 2, that will be 9, and the sum squares 171, 153 this. So, we can create MS. What is MS? SSR by degree of freedom, and your MSE will be SSE by degrees of freedom, and the quantity MSR by MSE will follow f distribution with the respective numerator and denominator degree of freedom. It is similar to ANOVA case. Okay. Here what you are finding out, your R square is saying that your model is not good, but your F statistics is saying that the p value is how much here, 0.034. It is less than 0.05. Then what is the difference between this vis-a-vis this? What we are testing here? Okay. I think you can understand this thing also in reference to ANOVA. So, when you make this type of ANOVA table, our null hypothesis is that beta j equal to 0 for all j. That means there is no regression coefficient which is significant, and our alternative hypothesis is that there is at least one beta j for at least one beta j zero one, like this. So, that means if beta 0, beta 1 or any one of the beta parameter are significantly contributing in explaining the variability of y, then this H 0 will be rejected. R square is a consolidated measure, that how much variability of y you are able to explain. If it is 52%, you are not happy, you want 90% or more, but 52, even if 52% is explained, but that means some parameter, some of the IVs, independent variables, they have importance, they are explaining that 52%, it is not 0%. So, as a result, you are doing another test collectively, you are basically checking that there is that influence of all the regression parameters are 0, and alternative hypothesis is at least one of the regression parameters has effect. Now, this is the case, and under this situation our test says that my model is fit. Okay. So, it is not contradictory, it is R square, it is the overall measure. It is saying that yes, overall you may not be happy with the explanation, because you are not able to explain the total variation of the y variable, but you are able to explain 52%. So, that means some variables are contributing, and that is being tested here. If this is the case, then definitely we want to test the individual parameters. Now, collectively this F test is saying that there are some parameters which are contributing. F test is saying. R square is saying that overall variability explanation is poor. Now, because of R square, you may discard the model, absolutely no problem, you may not go further, but as 52% variability is explained, 52.7% variability is explained. So, then you may be interested to know also that it is something which we know now. So, I want to know which variable is contributing towards this direction. So, then next topic is test of individual parameters. Okay. So, individual parameters mean beta j. Zero, 1 to p. You have seen earlier that the beta cap is the estimate of beta. So, that means expected value of beta j will be beta j. Okay. Now, we can also create one statistics like beta cap j minus expected value of beta j cap by standard error of beta j cap. This will follow t distribution, n minus p minus 1 will be the degrees of freedom. Okay. So, that means this quantity becomes beta j cap minus beta j by, now this value S e beta j, can you remember what will be this value last class? S e square into C j j. In last class we have seen this one C j j, where C is nothing but x transpose x inverse. This will be a matrix of P cross P, and somewhere in the diagonal line that jth variable is there, this you are taking as Cjj. Fine. So, this we are saying it will follow this distribution. Now, this will follow T distribution, we are saying this follow under H0. So, we will test some hypothesis here. What is this H0? H0 is beta j equal to 0. Okay. Then H1 is beta j not equal to 0. What is the difference this versus F test? Here we are saying beta j equal to 0 for all, and alternative at least one is not 0. Here you are not testing collectively, you are testing for a particular variable x j, its contribution. The contribution is beta j. So, you are saying H0 beta j equal to 0 and beta j not equal to 0. We are not considering the other variables, getting me. So, under this case what will happen to this, that beta j cap minus beta j by S square C j j will become beta j by S square C j j, because beta j equal to 0 under H0. So, you are putting beta j value 0. So, this is what is t value you find out in any software. If you run, you get a what I can say that output. In that output you will find out one table, individual parameters, then the standard error, then t values. This t value is this beta, this one. Now, this quantity follows t distribution. What does it mean? It is a two-tailed distribution. So, this side let it be alpha by 2, this side also alpha by 2, then this is t n minus p minus 1 alpha by 2, t n minus p minus 1 alpha by 2, this is minus, this plus. So, if your computed t, this is the t computed, beta j cap by its standard deviation, if this one falls here or here, either the left extreme or right extreme, that the rejection zone, then H0 will be rejected. So, this is our acceptance zone for H0, and this side is rejection zone for H0, and this is also rejection zone. Correct. So, let us see what is the, I think you will be able to do this one because all the informations are with you. all information. We have already seen beta j, cjj also given to you, AC square is known to you, everything is known to you. So, you will be able to compute this. Now, this is the parameter test table. In this table, you see this is the predictor or explanatory variables or independent variable. One is beta 0, that is the constant term, absenteeism, machine breakdown hours. Now, we have seen that beta 0 is 130.22, absenteeism minus 1.24 and machine breakdown hours minus 0.30, that since we have given. These are the standard error. Okay. The standard error is this. Just let me see this. You see this. This is C matrix. Okay. In this C matrix, how these things are coming? You can write that C is X transpose X inverse. Okay, this is inverse. This one I have written in Excel. This is X transpose X inverse. Okay. So, this value is 40.9. I am writing only the diagonal one, 12, 0.12. Off diagonal elements are also there. So, then this one is C and your standard error of beta j cap, this is AC square CJJ its square root. Achha, what is AC square value we got? AC square, I think I told you that 17.08. So, AC square is 17.08, correct. So, if I want to find out standard error of beta 0 cap, then you will be writing 17.08 into what you multiplied? 40.9? 40.9. So, this value we will get some value, this value will be basically 26.43. So, similarly, standard error of beta 1 cap, it will be 17.08 into 0.012, this value will be your 0.448. And standard error of beta 2 cap, this is also same, 0.8 into this one is also 0.0201 2 and some values are there, okay, 0.125 or 4 something like where there, and this one is 0.058. Here it will be 0 like this, some rounding errors effects are there. Once you know these values, that ACs are known. So, what will be your T values? Corresponding T values, can you not find out? T values are estimate by standard error. First one estimate is 130 point what? 22 beta. Okay, I think you can still remember this one, 130.22 minus 1.24 minus 0.30 that I have given you earlier. So, this is the beta j, beta 0, beta 1, beta 2 all cap estimate value. So, this divided by standard error is 26.43. Second one is how much? Minus 1.24 divided by standard error 0.448. Then third one is your minus 0.30 divided by 0.5458.
And expected value under H0 you are taking that it is 0.
It is 0. H0 is saying that beta j equal to 0, and then this value, all these values, this value will become 4.93, this is minus 2.78, this is minus 0.65, correct. If this is the case, If this is the case, then you see one thing, that this is my t distribution. So, I am creating my acceptance zone. This is t n minus p minus 1 mean 9, alpha value let it be 0.025, that is 0.0205 by 2. This is minus T9 0.025. This value will be 2 point, I think 262. So, what is your beta 0 value? 4.93. So, 4.93 means somewhere here. So, 4.93. Second one is minus 2.78, somewhere here. Third one is minus, this is my 0, minus 6 point, minus 0.65. So, you have seen this is your rejection zone, rejection of H0, rejection of H0, acceptance. Now, this one is related to beta 0 cap, this value, this is beta 1 cap value related to this is beta 2 cap. Beta 0 rejected, beta 1 also rejected, only beta 2 is accepted. So, that is why what happened, at least one of the variables, there are two variables x1 and x2, constant is the intercept term, we are interested in these two, concept is also there, it is also significant. So, beta 1 is significantly contributing. If it is contributing, what is its contribution? That also you may be interested to know. So, you also be interested to know that what will be the contribution of x2. This is the parameter says that if 1 unit change in x1 is there, beta 1 unit change in y will be there. But from regression SSR point of view, SSR can be your SS beta, that is beta 1 also, or x1 I can say SS x1 and x2, although those variables constant, they are also contributing. So, you think if you can find out, actually in regression we hardly require this thing, we require this beta values. Okay. So, this is what is our parameter test. So, essentially I told you that R-square, Rsquare and test of parameters, test of beta g, j equal to 0 to p. This is the case. After that, you have to do the test of assumptions. Your model is fit and you are considering the model, then only the individual parameters and test of assumptions are required. Otherwise, if you think that the model fit is not good, you are discarding the model, no need of fitting the parameter, test of assumption further. But when you accept a model, you must do the test of assumptions. I think test of assumptions we will consider in the next class. Okay.